Hi everyone. In this video we are going to learn about inverse matrices. By the end of the video you should be able to compute inverse matrices, but before we get there, let's talk about systems of equations because that's the theme of the chapter. So I want you to solve this two-variable system using as many methods as possible. So let's just talk about what those methods are. Okay, one, you can solve it like you learned in Algebra 1. You can use substitution or elimination. So on your own, you can go ahead and try doing that method. The second method we learned is to use Gaussian elimination. Gaussian elimination. Okay, which again, you can try on your own because we've already practiced that and learned that. There's a third method to solve this using some things we've learned in this chapter, and that is to set up a matrix equation. Which, to set that up, you're really going to think about multiplying matrices, but backwards. So you're always going to have your coefficient matrix, then your variable matrix, and then your constant matrix. Okay, which to recap what that looks like, it would be a matrix of, our first equation is 5 and 7 for my x column and my y column, and then 6, 9. Okay, my variables are x, y. And that equals my constants, which are 27 and 36. So it kind of looks like the equations put into matrices, and you can confirm that this is the correct matrix equation by actually multiplying our matrices. So remember, it's always row by column. So if I wanted to go and multiply those, I'd multiply corresponding entries. So 5 times x gives me 5x. 7 times y gives me 7y. Okay, so that's why you kind of turn the variables into a column matrix here, because if you're going backwards for multiplying, you multiply row by column, that'll give you what you want. So this is the augmented matrix that represents the equations. So I put my signs back in, and that row equals 27, which gives you the equation you want for the system. If you repeated this process of multiplication with the second row in this column, you would get the second equation. But that's kind of a review. Now I want to talk about how you solve a matrix equation without just solving the system of equations with substitution or elimination. Okay, for a second, I want to go through the thought process you should be going through right now. Do not write anything down because I'm going to erase it. Okay, so if I were you, I'd probably be thinking, okay, these matrices are being multiplied, so to undo multiplication, I'll just divide by the matrix. Okay, because multiplication undoes division, right? However, we do not divide matrices, so that is why we need to learn about inverse matrices, because the inverse is what undoes whatever is bothering a variable, for example, and inverse matrices will undo this matrix, but we don't really do what you think of as traditional dividing. This is something I'll explain more in class because it's kind of complex. But for now, just know you don't divide matrices. Instead, to get rid of this, we're going to multiply by the inverse matrix. So I'm going to write this down, but we have to know what the inverse matrix is before we can actually solve this equation. So multiply by the inverse matrix. Okay, so let's go ahead and figure out how to find an inverse matrix, and then we can finish solving this problem. Okay, so what is an inverse matrix? This is the formal definition. Essentially what it says is if you have a matrix A, the square matrix, n by n, so that means like 2 rows, 2 columns, 3 rows, 3 columns, 4 by 4, whatever it is. Okay, then there's a matrix A to the quote-unquote negative first, but that means A inverse, for which if you multiply A inverse by just A, you will get the identity matrix. That's what I stands for. I is the identity matrix. Or if you do it the other way around, so A times A inverse, you'll also get the identity. So in order to understand this definition, we need to know what an identity matrix is. So think about what an identity means outside of matrices. Basically, this is an example that you should be familiar with. Anything multiplied by 1 will not change the value because 1 is the multiplicative identity. So what that means is 1 is the identity, because if you do like 1 times 5, it'll still be 5. That 1 didn't change anything. Or if you multiply 1 by negative 1/3, it'll still be negative 1/3. That's the identity. So the reason if you multiply A inverse by A, you'll get the identity is because they undid each other. So like, for example, if I have 3 halves and I multiply by 2/3, this is an example of applying inverse operations. 3 halves and 2/3 are inverses of each other because here you're dividing by 2, but then here you're multiplying by 2, so those would cancel. Here you're dividing by 3, but here you're multiplying by 3, so those would cancel. And if you apply those inverses to each other, you'd get 1. Same idea here. If you multiply two inverses, you won't get 1 because it's a matrix, but you will get the identity matrix, which is like the identity of multiplication. So the identity of multiplication is 1, that's why you get 1 here. The identity matrix of a matrix is kind of like that, except it's a bunch of 1s and 0s. So for a 2 by 2, an identity matrix is 1, 0, 0, 1. For a 3 by 3, the identity matrix is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now, I'm just telling you this fact right now. You should never just believe me. Go ahead and multiply a 2 by 2 matrix by this, and nothing should change. Think about why that is. Or multiply a 3 by 3 matrix by this, and it should stay the same. This is something I'm going to leave for you to confirm. Okay, if you want confirmation of it, here's a 2 by 2 matrix. 2, 3, 4, 5. Multiply this by this and see if it changes. Okay, 3 by 3 matrix can be like this. That is a 3. Multiply it by the identity and see if it changes. So do like 1, 2, 3, 4, 5, 6, 7, 8, 9. Multiply it with this. You can do either way, and it should stay the same because it's the identity. Okay, we're going to talk about how you find an inverse matrix. So before we do this, I want you to practice the multiplication. What I want you to do is compute A times B and B times A on your own, and I will come back with the answer. Okay, I hope you paused the video and did that on your own. If you did, A times B should give you this matrix here, and B times A should give you this matrix here. And what do you notice about those matrices? You should notice that you got the identity matrix for both products, which has to mean then, by definition of an identity, if you multiply two matrices and you get the identity matrix, that those two matrices are inverses. So that means A is the inverse of B and B is the inverse of A. So if I call this A, this would be A inverse, because A times A inverse gives you identity. Okay, or I can do it the other way around and I should still get the identity, which is what the definition says. Okay, the reason I had you do this is because I want you to notice some patterns between inverse matrices, because they kind of look the same. Like these two numbers are exactly the same, these two numbers are exactly the same, and these two numbers are only different by sign. So in some sense, you sometimes may be able to recognize an identity matrix. Okay, and I'm going to teach you exactly how to find them, and you'll see why there are some similarities. We're going to go back to method 1 in a second. Let's start with method 2. Okay, so this is just the procedural process for finding an inverse matrix, starting with a 2 by 2. To find the inverse of this matrix, in general, actually, maybe I should give you a general rule first. Let's say this is matrix A, B, C, D. And I want to find the inverse, which that's what that -1 means. In order to do that, you're going to take 1 over AD minus BC, and you're going to multiply it by the matrix D, negative B, negative C, and A. Okay, so if you take a look at what happens to the matrix itself, you switch these two, so D goes here and A goes here, and then you negate B and C, so they become the opposite. Okay, and then you're going to multiply that new matrix by 1 over the product A times D minus the product of B times C. Okay, I'm going to leave this one for you to do on your own, but I'm going to apply this to the previous problem so you can see where that comes from. Okay, so if I want to find the inverse of 3, 2, 5, 3, okay, I will start by writing my matrix out. So remember, you're going to switch A and D. So these are going to switch. Now, they're both 3, so I can't really switch them because they're the same, but you get the idea. Those would switch. And then I'm going to negate the other diagonal, so these two numbers are just going to become the opposite. So this will now be -2 and -5. Okay, but notice that wasn't the inverse matrix. So it kind of looks like what I got. It looked like I switched them and negated them, but wait, the signs are all wrong. Why is that? I bet you were all wondering that when I initially introduced these formulas, right? Like, that doesn't look the same. And that's because of this multiplied factor on the outside. So you're going to multiply this by 1 over AD minus BC. So this is A and this is D. You multiply those, you get 9. Minus BC are these two numbers. which gives you 9 minus 10, which is really 1 over negative 1. So really what I did is I multiplied this whole matrix by negative 1, and that's why all the signs, while the matrix looks kind of right, all the signs look wrong. It's because that multiplied factor on the outside was negative 1. So if I distribute that negative 1 out, then I'll get the matrix I wanted, which is negative 3, positive 2, positive 5, and negative 3, which we've already confirmed is the inverse, because if you multiply those together, you'll get the identity. Okay, so this is just a formula. You have to know to find the inverse of a 2 by 2 matrix. For a 3 by 3 matrix, the formula is really, really nasty, so that's why I'm giving you a method 2 to find a inverse matrix. And this will work for a 2 by 2 or a 3 by 3 or any matrix. That's why it's kind of nice, is you don't have to memorize different formulas for each kind of matrix. You can just do this method every time. That method is using Gaussian elimination. Gaussian elimination does everything, I guess. I'm going to leave the example I gave you for you to try, and I'm going to try Gaussian elimination on this matrix here, that 3, 2, 5, 3 thing. 3, 2, 5, 3. And in order to get an inverse matrix, I want when you multiply the two together that you get the identity matrix, which is 1, 0, 0, 1. So another way to find the inverse of a matrix is to do Gaussian elimination on the original matrix such that you get 1s and 0s over here, but you're going to perform Gaussian elimination to this whole thing. So whatever happens to this side when you get 1s and 0s over here, this side should be the inverse matrix. So all I want you to do right now is perform Gaussian elimination on this whole 2 by 4 matrix, but I want you to do it in such a way that you get 1, 0, 0, 1 here, and see what happens. I'm going to pause the video so you can try that on your own and practice Gaussian. Okay, so I went through the process, I made mistakes, I corrected it. I started by doing R2 minus R1 to get this blue matrix. Okay, then I did 2R2 minus R1 and put it in R1, and I got this red matrix. Then I did this rule here to get the black matrix. Then I finally just had to multiply the last row by negative 1, so R2 by negative 1. And I got the identity matrix on the left, and therefore my inverse matrix is on the right, which we can confirm because we already know the inverse of our original matrix. So our original matrix was 3, 2, 5, 3. Our inverse matrix by Gaussian elimination is negative 3, 2, 5, negative 3, which again we confirmed up here is the inverse of our original matrix because when you multiply them, they undo each other. Okay, so anytime you have a 2 by 2, a 3 by 3, a 4 by 4 matrix, you can always put the matrix, original matrix on the left, the identity matrix on the right, perform Gaussian elimination to kind of switch and get the identity matrix over here, and the inverse will be on the right. So those are two methods. If you have a 2 by 2, you can use this formula, or you can do Gaussian elimination. If you have a 3 by 3, you're going to want to use Gaussian elimination every time, or if you have a 4 by 4 or 5 by 5. I know I said a lot in this video, and I know you probably have a lot of questions about, like, why does this work? Why does that work? Please hold on to those, and we'll talk about that more in class. But there are plenty of problems for you to try. So you can try this, this, and this for some practice. I do want to go back to the point of this all, and the reason you learn about identity matrix is to solve a system of equations. If I want to undo this matrix that's bothering my variables, now we learn to undo that, you want to multiply by the identity. In order to get the identity, if I call this matrix A, I would have to multiply this by A inverse. So if I multiply this matrix by its inverse, those will not necessarily cancel out, it won't go away, but if I do A inverse times A, I'll get the identity matrix times XY. Okay, but whatever I do to one side, I have to do the other. So I'd also have to multiply this by A inverse. So that would equal some new matrix over here that I don't know right now. The reason this helps is because now, if you multiply these back out, I'll have 1x plus 0y equals some number. In my second row, I'll have 0x plus 1y equals some number. I don't know what these numbers are for this problem right now, but those numbers are going to come from, if I multiply by the inverse over here, I also have to do it over here. So that's where I'll get those numbers. With more time, I could complete that problem. Okay, so that's why we need to know identity matrices, is so we can solve matrix equations. So please, I know that was a lot of information. Come with questions. You can finish this problem on your own by actually finding the inverse matrix and multiplying both sides by that matrix to get the identity and to get your solutions.